The factor theorem for polynomials. Now, when we're looking at something a little more complicated, it helps to keep it in terms of what we do know. We do know what a factor of a number is. So when looking at if 5 is a factor of 24, we know if we have 24 divided by 5, we do not end up with it going in evenly. We have a remainder. So we know 5 cannot be a factor of 24. However, if we take 25 and we divide it by 5, we know that goes in evenly, goes in 5 times, and we get a remainder of 0. Now the same is going to be true of polynomials. Is x minus 2 a factor of this? Well, now of course we could factor x squared plus x minus 6, but our polynomials are going to get more and more complicated, and we would like to be able to tell if something's a factor without trying to factor it, especially when we get to quartic and quintic polynomials. So we can divide this polynomial by x minus 2 and see if there's a remainder. And we can do that 2 ways. We can either use long division or we could use synthetic division. So let's just do a quick review of how to do it both ways. So x minus 2 into x squared plus x minus 6. We want to know x times what is going to give us x squared. So x squared divided by x. We know that's going to be an x. X times x is going to give us our x squared, which is why we chose that. And then x times negative 2, which is negative 2x. Now we need to subtract them. But I like to think of subtraction as add the opposite. It's a little bit easier to do. So I'm going to change the signs here. That's a negative now, and that's a positive. Go ahead and add them, and I have a 3x here. And then bring down our negative 6. And we say x times what gives me 3x. That's going to be a 3. 3 times x is 3x. 3 times negative 2 is negative 6. We're going to subtract or add the opposite. And I have a 0. When I have a 0 remainder, that tells me that x minus 2 is a factor of x squared plus x minus 6. It also tells me, just like with numbers, that x plus 3 times x minus 2 is going to give me x squared plus x minus 6. So x minus 3 is also a factor. Now let's do the same problem using synthetic division. When we use synthetic division, whatever makes this 0 over here, so I take the opposite of whatever number this is, in this case 2, and I'm going to go ahead and write the coefficients of my other polynomial. 1, 1, negative 6. 1, 1, negative 6. I bring down this 1. 1 times 2 is 2. Add that. 3. 3 times 2 is 6. Negative 6 plus 6 is 0. So again, I get a remainder of 0 using my synthetic division. So if I look at this in factored form, I can see that both x minus 2 and x plus 3 are going to be factors of this polynomial. Now let's take a look at the factor theorem. So if I take this same polynomial and write it in factored form, which is just f of x is equal to x minus 2, x plus 3, it's exactly the same, just in a different form. Same value, same polynomial. This is just written in factored form, and this is in standard form. Now if I take a 2 and plug it in, well, I know if I put a 2 here, I'm going to get out a 0, because 2 minus 2 is 0. So if I look at my 2 up here, I should also expect to get a 0. So 2 squared, which is 4, plus 2 minus 6. So 4 plus 2 is 6 minus 6, and I get a 0. So what this says is if I take a value and I plug it in or substitute it into my equation, and I get out a 0, I know that the opposite, this is going to make a factor. So the opposite of this. So x minus a is a factor. IFF, that's if and only if, f of a is equal to 0. So if I think something's a factor, I can take f of a and see if it is a 0, and then I know x minus a is a factor. So this if and only if means this can go both ways. If I know x minus a is a factor, then I know f of a has to be 0. If f of a is 0, I know x minus a is a factor. So if negative 3 is 0, I know x plus 3 is a factor. If f of 2 is 0, I know x minus 2 is a factor. That's the factor theorem. Is x plus 3 a factor of x cubed plus 27? Well, we can do this two ways. We can do a division problem and see if we get a 0, then we know it's a factor. Or we can look at f of negative 3. Because by the factor theorem, if f of negative 3 is 0, then I know x plus 3 must be a factor. So let's first look at this. F of negative 3, I'm substituting a negative 3 in for every x. Negative 3 cubed is going to be a negative 27, and f of negative 3 is a 0. So x plus 3 is a factor by the factor theorem. Now let's look at it this way if we wanted to do that division. X cubed plus 27 divided by x plus 3. And you could do this either with synthetic division or with long division. I chose synthetic because it was a little faster. So I put a negative 3 here. Now notice I have some placeholders for my x squared and for my x terms that I don't have up here. So 1 in front of the x cubed, a 0 for x squared, a 0 for x, and then my 27. Bring down the 1. 1 times negative 3 is negative 3. Add them, negative 3. Negative 3 times 3 is 9. 0 plus 9 is 9. 9 times negative 3 is negative 27. Add them, and I get a 0. So because there's no remainder, I know that x plus 3 must be a factor. Now I can rewrite this as a whole polynomial, as back to my original x cubed plus 27. So I can take this part right here and rewrite it as what's called a depressed polynomial. So x squared, from that 1, I'm going 1 less because I started out as x cubed and I found out that x plus 3 was a factor. So x cubed minus 3x plus 9. When I multiply that by my factor, I get back to my original polynomial. So this depressed polynomial is very handy, especially if you needed to factor this more. This, however, doesn't factor. So if I'm only finding my rational roots, I know I'm not going to have any more rational roots if I can't factor this. So x plus 3, and then I have parentheses, and this doesn't factor. And I can tell it doesn't factor by looking at the discriminant. So when I do the discriminant, I can find actually that it's negative, and I'm going to get some imaginary numbers. So this would be in factored form. Is x minus 1 a factor of f of x? So here I have f of x, and I've got a big, long polynomial here. So it's not just easy to factor it. I know if it's true, the remainder has to be 0. I also could substitute a 1 in there and see if I got a 0 out by the factor theorem. So let's do that first. Substitute a 1 in there. 4 times 1 to the 4th power minus 2 times 1 to the 2nd power plus 1 plus 1. So I just substituted a 1 in for all of my x values, and I ended up with 4. So because I ended up with a remainder, I can see that x minus 1 is not a factor. But let's go ahead and look at my division problem. Let's say I decided to check to see if it was a factor by seeing if my remainder was 0. Again, I used synthetic division. I needed a 0 for my x cubed placeholder. So I have a 1 right here. 4, 0, negative 2, 1, 1 come from my coefficients. And I bring down the 4. 4 times 1 is 4. Add them. 4. 4 times 1 is 4. Add them. I have a 2. 2 times 1 is 2. Add them. 3. 3 times 1 is 3. Add them. And I get a 4. I get the same value for my remainder as I did when I substituted a 1 in. I got that 4. So, by synthetic division, I am thinking I'm able to get what f of 1 is using this division problem. So that comes to the remainder theorem. This happens every time. When f of x is divided by x minus a, the remainder is f of a. So if I have a big ugly polynomial and say I wanted f of 5, well, 5 to the 4th power is going to be a really ugly number. I could just use synthetic division, put a 5 in, and find out what the remainder is. Now let's take a look at why this works. So this is why the remainder theorem works. And I think it's important to know why we're doing things. So I don't think this is anything you need to take notes on, but see if you can follow through why this remainder theorem works. So I'm going to take you back probably to 4th grade when you're doing a division problem and you're writing the remainder as a fraction. So if we have 5 into 13, that goes 2 times 5 is 10, and I have a 3 left over. Now I can write that as R3, or I can write that as a fraction and 3/5. So you don't have enough to go in another whole time, but you have 3 out of 5. So we can rewrite this as 2 to the 3/5 times 5 equals 13. We can do the same thing with polynomials. So x minus 1 into this polynomial. You've seen this polynomial before. And so I just did it using long division. Now, as I went through the long division, I got a 4 at the end. I can rewrite this 4 as a fraction, 4 over x minus 1. So x minus 1 times this, and I got this x minus 1 from over here, just like that 5 came from there. So x minus 1 times this, when I multiply it, it's going to give me back to this original polynomial, this f of x. So I have a fractional part right here. Now let's take this and move it over here. This is the same thing as f of x. I multiplied my answer up here by x minus 1, that whole thing. That's the same thing as this original polynomial. Now what I can do is I can distribute this x minus 1 to this part and to this part. So that's what I did here. X minus 1 times this plus x minus 1 times this little fraction part right here. Now the reason I do that is because x minus 1 over x minus 1 is just 1. So I just have this 4 hanging out here. So I have x minus 1 times this whole thing right here plus 4. Well, when I'm looking for f of 1 and I substitute a 1 in for that x, I have a 1 minus 1, which is going to give me a 0, times this section of it, when I substitute a 1 in, plus 4. So this is going to give me a 0, and I end up just with a 4. So that's why the remainder theorem works. When I do that division, that 4 is the only thing that's left over, and I'm going to get my answer of f of 1. Because remember, this is the same thing as this, just written in a different form. So it's great if you followed that, and let's look at another example using that remainder theorem. F of x is equal to 3x cubed minus 2x minus 1. And we want to find f of negative 3. Now we could substitute a negative 3 in there and figure it out, but we're going to use the remainder theorem. So I know if f of negative 3 equals the remainder after dividing this f of x by x plus 3. So here's my division. I have a negative 3. I wrote my coefficients. I have a placeholder for x squared. Negative 2, negative 1, bring down the 3, negative 9, add, multiply, 27, add, 25, times negative 3 is negative 75, and look, negative 76. Now that was a lot easier than doing 27 times 3 minus 6 minus 1. And it can be even more so, but I know negative 76. If I were to plug a negative 3 in there, I would get out a negative 76. Now let's also try f of 4. Now 4 cubed is a pretty big number. So I'm going to put 4 here, and I have my coefficients from above. Bring down the 3, 12, add, and I have 12. 12 times 4 is 48. Add, and that's 46. I'm going to do 46 times 4 over here. That's 184, and that's a lot easier than doing 4 cubed over there and multiplying it by 3. 46 times 4 is 184, and then I subtract 1 from this 1 up here, and I have 183. So that means if I put a 4 in here for x, I'm going to end up with 183. F of 4 is the remainder after dividing f of x by x minus 4. Now you can use that remainder theorem to help you find values that are a little more difficult to plug in.